Hello, hello everyone. It's been a long week. I don't know if you can tell, I ate my surfboard surfing. Had a nice car. I think it's getting better now. Today we're gonna continue building a robot dog as we do in this channel. And we have our to-do list here. We're gonna talk about what we're gonna do. I think I'm gonna sit here for the next maybe 4 hours and just work on this. And we should be able to do a lot of serious progress. Now, before we get started, I want to share some cool things that I saw through the week. So maybe you'll find them interesting. Obviously, this week the biggest thing was, I think, at least in AI, in tech, in San Francisco, the whole OpenAI drama. Their CTO leaving, bunch of senior people leaving, them becoming a for-profit instead of non-profit. So a lot of things happening there. New Llama 3.2 model. This has nothing to do with building a robot, just things that I think are cool. Also, I wanted to introduce you guys to Brian here, Brian Mercado. I actually do not know Brian personally. I know of Brian, and we have some friends in common. He also went to Waterloo. We went to the same school. This guy is interesting because he built this company, his website called Glove Engineer. No, sorry, that's not it. Glove Engineer. It's like a search engine. And I never fully got it, but they seem to get a lot of traffic. And so you can search here, for example, quadruped robot actuator, and this is a free version. And it starts to give you images of things. So almost like a more powerful Google Images search. And so once you see something that you like, I actually happen to not like anything, but it gives you a description, you can open the link. So it's kind of like a different search engine. And I know, I think they are doing pretty well. Anyways, Brian apparently has moved back to Waterloo, I think, from what I can tell from Twitter. And he's building these robots here. Which is very similar to a Coma body, which is like George Hott's robot here, which is like, they have this whole thing at Coma of like, oh, you don't need humanoids, that's like overbuilt, and like keeping things simple and not adding complexity before it can actually deliver value consistently. I think that's kind of like the premise. These things are pretty expensive for what they are, in my opinion. So 1,000 for the body, and then you gotta buy a Coma to put on top, and those things are another 1,000 a little extra. So $2,000 for what it's a pretty simple robot. Brian seems to be building them. I think I'm sure his BOM is much cheaper. Anyways, the reason why I'm bringing this up is because like he answered the question. People are like, oh, if you're building these robots, what's the purpose? Why are you building these robots? And he put out this really short essay here. You know what? I'll put all these links in this document here. We'll make a follow along here. And so if you're interested, I'll put the link to this on the video bio, and you can just go see it for yourself. Brian is a cool guy to follow. You should follow him on Twitter. But it's like, what are the robots gonna do? People often ask me what these robots are gonna do, and the honest answer is I don't fully know yet. But that's precisely the point. Throughout history, many groundbreaking inventions emerge not from a predetermined purpose, but from curiosity and experimentation. And then he lists some examples here, some good examples, right? So the discovery of penicillin by Alexander Fleming. He wasn't searching for antibiotics. He noticed that a mold contaminated his petri dishes was killing the surrounding bacteria. And it was this unexpected observation, born from an open mind and willingness to explore, that led to one of the most significant medical breakthroughs in history, which is, I think that's basically exactly what happened. The invention of the microwave oven by Percy Spencer. This was news to me, I didn't know. It was an accident. While working with radar technology during World War II, he noticed that a chocolate bar in his pocket had melted. Intrigued, he experimented with popcorn kernels and eggs, eventually developing a new cooking appliance found in millions of homes today. So that's pretty cool. This made me think, if a chocolate bar in your pocket is melting from radio waves around you, what about your organs? But anyways, and then X-rays by Wilhelm Röntgen. Experimenting with cathode rays, he observed a fluorescent glow on nearby screens, even though it was shielded. His curiosity led him to investigate this phenomenon, resulting in a tool that revolutionized medical diagnosis. These innovations weren't the result of following a strict plan. They were born from exploring the unknown and embracing unexpected results. By integrating these unique, non-humanoid robots into our environment, we're creating opportunities for similar serendipitous discoveries. I trust that as these robots become part of our daily lives, we'll find interesting and meaningful roles for them. The roles we might not have imagined from the outset. This project is about inspiring wonder and pushing the boundaries of how we interact with technology. It's about embracing the unknown and allowing creativity to lead the way. Sometimes, the most remarkable innovations happen when we're simply exploring what fascinates us, without knowing exactly where it will lead. And I thought this was super relevant to what we're doing here, here with the robot dog. I think if you go back to video number 1, I had this thing of like, oh yeah, we're building a robot, we're calling it Antarctic because we want to send it to the Arctic. And why the Arctic? Because it's like the closest boundary to Mars that we have. It's very remote, we'll get a lot of clicks. But that's no real utility. We just thought it was fun, and something might come out of it. And I do think we're gonna do a lot of firsts along this project, things that haven't been done before. One of the first tasks that we're training this robot for is to actually dig a hole in the ground. I haven't seen a robot do that before. We think that's cool. We're gonna do it. We might learn something new. So I thought that was cool, and I also think this is a very different approach to things. I think a huge role model for me has been Elon, and he seems to think of things from very first principles and what makes sense in economic sense, and using physics to see where things are today, but where could they be with technology and physics, and push them to that. But this is more of like, experimenting, more of like, just whatever is fun. It feels much less optimal. As an engineer, it feels like more of an art than a science. But there's so many inventions here, very important inventions here that obviously change the world. And so I wouldn't discard this approach. Plus it's fun. When every time I'm like, I'm building these, to my engineering friends, the first question is like, why? What's the point, right? So I think this was good. So put the link in there in this document. I'll put it in the description of this video. I'll keep populating this document. We'll keep one document for the entire of this series till we have the dog working. And you can come in and you can probably even leave comments if you want to leave comments. So that's cool. Another thing I saw was cool, I thought was cool, was this AnySkin project. Let me add it right now. So it's a plug and play skin sensing for robot touch, right? So it's a very simple, like open source, basically sensor array that you can put on a surface, and it can map touch, basically pressure, skin sensing. That is pretty cool as an interface, but also to allow your robot to interact with the environment and sense its environment. And of course, the application they have in mind here is a gripper that's picking up something. When you pick up something, as humans, we're very conscious of like how much pressure to apply, right? Because if it's something hard like an AirPods case, you can apply some pressure. If it's something very squishy, like I don't know, like a banana or something, or a cotton ball, you wouldn't apply as much pressure. And these kind of things, hard to teach a robot, but now if they have some feedback loop in this case being like pressure sensing or touch sensing, it enables new applications. So I thought that was cool, and of course it's open source, so I think at some point we're gonna have to play with these. So that's very cool. Another thing, if you haven't seen this yet, the Mr. Beast memo, how to succeed at Beast Productions. This one's also very cool. I recommend reading these. It's a 36 pages of like kind of like the handbook for new hires at Mr. Beast company. I think it's interesting because one, as you know, as someone who wants to build a company, it's like you probably should be able to distill your vision for others in a document like this. But also, it's really cool to see how they operate. They have a lot of non-traditional things here. They have things of like how to look for good, talented people, and examples of how to be like a high agency operator. I think that's cool. So I highly recommend reading that. This is not as related to what we're doing here. I will add, by the way, just in the Mr. Beast, while we're talking about Mr. Beast, originally, I did say we wanted to send this robot to Mars. Obviously, we can't go to Mars, maybe Antarctic, we'll see. The reason why we wanted to do something like that is to get clicks. The reason why we want to get clicks, it's not because like we care of like, oh, if people watch it. Ultimately, if you just want to get clicks, there's probably way easier ways to get clicks than build robots, right? Mr. Beast never built robots. That's a very expensive and high effort way of getting clicks. Not saying that Mr. Beast doesn't do high effort things, but building robots is probably more high effort, I would argue. Willing to be proven wrong, but the reason why it's interesting, it's because YouTube gives you money for clicks, obviously, right? And so I think a lot of these new robot applications that, the purpose is not super clear yet, it's hard to monetize. And so it's hard to generate revenue, it's hard to build a company around them. Other than like, oh, trust me, in 10 years in the future, we'll make it work, just give you us money, which it's kind of like the path that a lot of the autonomous driving robots took. But a lot of like smaller, or like just people building at home like me, like we cannot take that path, right? No one's gonna give us money to build this robot. But we can fund it through YouTube, right? So if we can get clicks on YouTube, we can fund this robot. And so that's kind of like part of like my motivation for uploading these videos. I also personally am really into the idea of creating content, but if we ever get to the point where these videos here are making any money, all that money is gonna go towards the robot, and so that's very exciting. We're gonna be able to do cooler, bigger things. There's a scenario, there's a timeline, there's a scenario where like we get so many views that we're generating enough money to hire people and like kind of like build this lab where we like just test new robot ideas, and eventually maybe there's a business, maybe there's not, but if we're doing things that are interesting, that could be interesting. My other thing was that I think there's a path to building like a robot sports league that could be fully monetized just by just as an entertainment company, and it wouldn't be robot sports, it would be robots versus human sports, and this opens the door for all kinds of new different sports. Like imagine playing tag against a robot. Imagine playing paintball against a robot. That's like a whole another level of difficulty. Human versus human, who's the best human? Sure, that's at paintball. That's one thing, but how many humans does it take to be a robot at paintball? That's interesting. I feel like I would watch that. Another interesting one here. I'm gonna put it right now here, and I haven't fully digested this one, but this is about the joints in our arms. So if you think about your arm, right, your forearm, we obviously there's two bones that run across it, right? And so these two bones are here, and let's say they run across like that, but then your arm can rotate 180 degrees. And how do two solids can rotate 180 degrees without colliding? This paper kind of like shines a light into that, and so that's very interesting from if you're building robots, it's very interesting from a packaging perspective of like what's possible. Obviously this looks like a very complicated graph, but very interesting read. I suggest reading that too. Okay, so another one that's interesting, this is an IEEE article. You can go to the article too. It's like it's a whole PDF, but I'm gonna put the link here. Just watch the video. This ball joint is interesting. This is not a new concept, this is from 2021, but it just got posted on Hacker News this week. And what's cool about these is that it's basically, with two motors, they're achieving 3 degrees of freedom. and it basically uses this kind of like this ball, this mesh ball with like almost like a sphere gear to achieve these motions. And so that's a very interesting joint that I am very tempted to, you know, maybe build one day. And all of these can be 3D printed. So I haven't seen an open source version of these, of 3D printed of these. Maybe we will create the first one. Here they talk about the theory of operation. It's actually, you know, it's not a hard concept, and it's super, super cool, super clean package. I like that. Okay, and the last thing I have before we get to work, start opening Onshape, because sometimes it's obviously there's the whole Tesla robotics, what do they call it? Optimus, the whole Optimus project. Tesla hasn't been training Optimus 24/7 for the past 130 days. So they have people generating training data day and night for this robot. And this basically is, you know, people standing in a room doing tasks with sensors to create data to then train a model. I thought this was interesting. If Tesla, you know, is putting this much effort into these, think of all the other humanoid robot companies that are out there. So I think there's a business opportunity here to basically just be the ones that create the data and then sell it to these other companies. Because, you know, companies like, I don't know, who else is building humanoid robots? There's like, there's Figure, for example, Figure. I think Figure.ai, yeah, this guy, for example, all these companies will have to do the same thing, right? But it's the same thing with LLMs, the same thing with autonomous driving cars. There's a lot of data that needs to be created, a lot of data needs to be labeled. And so that's what Scale AI does, right? Scale AI labels data for automotive, labels data for OpenAI. You see the OpenAI logo. Actually, do they have the OpenAI logo? The OpenAI logo there. So these guys basically label data that eventually was used to create ChatGPT, was used for Waymo. Now someone's gonna do it for humanoid robots, and so that's a huge opportunity. I don't know if Scale AI is going that way. It will be super cool. I'm putting it out there, calling it now. Someone's gonna build a company in this space. It's gonna be cool. So I'm gonna put it there, and that's it. That's all I have in terms of cool things I saw this week. So now let's just get to work. Let's actually talk robot dogs. Let me disconnect the servos. This is the state of a robot dog. You know, we have 3 actuators now: joint, shoulder joint, hip joint, knee joint. It's looking good. Obviously, now that we have a working leg, and somewhat of a torso, we just need to replicate these 4 times, and we'll have kind of like a dog. Of course, last video we found out a lot of issues with our current configuration of torso. We need to clean up the torso. This was just the first pass. And I haven't worked on this since the last video, but this has been sitting on my desk all week. I've been looking at it, and I've been like trying to like just, you know, random thoughts of like, oh, how can we improve these? So I already have some ideas, and we can just get to work today. Let's rush through it. I feel like, you know, we've been like slowing down progress. I want to move faster. Anyways, with that in mind, let's check out our to-do list, right? So here's our to-do list. Last video, shoulder joint done. So I'm gonna start deleting things that were done. Body done, but I'm gonna say body improvements. So these are the improvements that we flagged. We need to figure out powering the servos. So I think we're gonna start with that now. Let me Arctic build a robot at home schematics. Wiring. Yeah, so let's get to work here. So first, let's figure out how can we actually. And by the way, I'm all over the place here, but just to recap, the issue with these was that we have 3 servos. These servos apparently pull, you know, up to 5 amps each, or could pull up to 5 amps each at like basically stall torque or stall current. And the Arduino Uno, that's the microcontroller we're using, and which we're also using to power these guys, only puts up 800 milliamps before there's some sensor that trips, basically overheats and it trips, when it trips, this microcontroller stops working. And so what we need to do is to power these servos from an external source so it doesn't trip. And so now we need to figure out the electrical for that. And so we're going to do that right now. I also happen to have a bunch of batteries from, I have a drone that I never learned to fly. I built a drone, flying was hard. I don't live near any place where I can fly, so it's hard to get some practice. So I've been putting that off for a while, but I do have a bunch of batteries, so I think we can put this battery in these robot dogs somewhere. And so right now I'm going to figure out how to use this battery to power the 12 servos that we have on board of the robot in a quick and dirty way, right? So let's just get an image of a servo motor. Yeah, so this is what our servo looks like, right? So like that, and then we have, my battery is a LiPo 6S. Yeah, let's say it looks like that. Right, so we have that, and then we have an Arduino Uno, which this is what a real Arduino Uno looks like. I have a knockoff version. Knockoffs just do just fine in my opinion. Anyways, so right now the way this works is, we only have one connection. This is PWM and power, and so that's why it's stripping. We need to also add a connection here, and might as well also have the battery power the Arduino, so the robot is like standalone on its own. It doesn't require a computer. And for annotation purposes, we have 12x of these. We have 12x servos, 1x battery, and 1x Arduino. And by the way, we also have other things to power. Not yet, but in the future we'll have other things to power, like a Jetson Nano to run like a ML controller. I'm not going to include it here because the Jetson Nano actually draws very little power compared to servos at their stall torque. So if we size this for the servos, we should be fine. Then it's more of a question of like, okay, how long do we want the battery to last for this robot? Yeah, so I think, with this current battery, I did some quick math, and I think it's going to be up to like half an hour if, worst case scenario. Now, how do you connect a 6S LiPo to a servo that it's looking for 7V volts? So 6S, basically 6S means 6 in series. So there's 6 LiPo, which means lithium polymer cells here connected in series. When you connect 2 cells in series, that basically their voltage adds up. So a LiPo, any cell, any lithium cell, because this is chemistry dependent, but any lithium cell will have, around 4.2 volts at its maximum charge. And then there's it's like an S curve, right? So it's maximum charge, it will quickly deplete, and then it will have a steady state, and then it will quickly drop. The steady state is somewhere around 3.8 volts and 3.6. Let's call it 3.6 volts. So at 3.6 volts, for each cell, we have 6. So 3.6 times 6, that's 21.6 volts. We cannot just directly hook that up to the servos, which are expecting 7V, because we would fry them. So we need a step-down converter, a DC to DC converter. So we need to put that in between here somewhere. And the Arduino will take 5V. So maybe we'll run everything 5V, so we can power both the servos and Arduino in a simple harness. And so this is actually a very, very, very simple problem to solve. We'll just go on Amazon, as we always do here. And what we're looking for here is called a buck converter. And like for $10, you can get something like this, right? So this is a constant current buck converter module. 6 to 40 volts, so it can take anywhere from 6 to 40 volts. Like I said, this LiPo 6S, it's like probably like 22 volts steady state, 4.2, and then 25 volts full charge. So this can handle it. And it can step down to anywhere from 1.2 to 36 volts, and we're looking for 5 volts, so this will work. And this can do up to 20 amps. We did say that each servo can pull up to 5, but I think that's like stall current. I don't think all the servos are gonna stall at the same time, so I think we can get started with these. So I would add these here. Oh. I would add our buck converter here. Let me just, so this is kind of like what our wiring is going to look like. So we have the battery here, buck converter here, and we're going to have, by the way, there's actually software to create nice electrical diagrams. None of them come to mind right now. Most of the ones I know are for PCB schematics, laying down PCBs. But I think they could handle this too. Just like, this is just easier. So this red line symbolizes I'm gonna call it a 5V bus. And so anything connected to this 5V line is 6 volts. Sorry, 5 volts. Yeah, this is 5 volts. Oh my god, so 5 volts, right? And so this is gonna be, I'm gonna measure the voltage in 6S. 6S, that's a very like hobby type of like labeling your voltage, but just to say, 6 in series, because like I said, 6 in series, that voltage will alternate depending on the state of chargers of your batteries. And so we can basically just get these and we'll fix all our powering issues, I think. We might eventually have to size up this thing, but it should work. Yeah. Now this is another thing that we need to package inside the dock, and this thing will also, just judging by the heat sinks, it could get a little hot. Our dog is plastic, something to keep in mind, but you know how we roll here, we just try things out, and if it melts, we'll upgrade it. And now the other thing is like just hooking things up like that. It's not like you can just hook it up. Like you can see here that we have a connector here, and you can see here that the buck converter takes, it's like crimped terminals. So we need to figure out how to do that connection. These connectors are used in drones very often, and they're called, this is an XT60. And the good news is that, let me add this to my card, or an XT60 connector, it's widely available. You can just get, you can just get a bunch off the shelf and hook it up. You might also want to get one with capacitors in there so it doesn't spark. Looks like there's none with capacitors. Okay, that's fine. We can just get these. And there's some male and females there. My battery is female, so our connector will be male. And then the ends on the other end of this connector are just wires, and so we can crimp those on the buck converter. So we'll also need these. So let me add that to card. And of course, we can probably get all of this tomorrow, which is pretty good. So I'm gonna add this to our schematic. Make sure we get it. And then out of the buck converter, you can see we only have 2 terminals, but we have to power 12 servos and 1 Arduino, right? So those are like 13 wires into one single terminal. Obviously that doesn't work. So we need some sort of bus bar. So, a bus bar like this would work, I think. That looks bulky. Bus bar, split connector, bus bar. So I'm just looking for bus bar 5B. Looking for, by the way the buck converter regulates voltage. I think it's just by a screw. Yeah, you see, there's these like screws on top of those like blue rectangles. You can just like adjust those, and it'll change the voltage coming out of them. And we can just use a voltmeter to see what voltage it's coming out. So we're just, yeah, we can do like a bus bar. I just want the smallest thing possible. I don't know if there's like a bus bar for jumper wires. Bus bar jumper. Like if not, we can just use that regular. We could also use a breadboard, I guess. I don't know what the current rating on a breadboard is, but I think we can just use a bus bar, kind of like these. This seems again expensive and big. But it, it would work. $20, man. M5, yeah, M5, that's huge. Bus bar, small. And on top of that, we'll just need some wire. I'm pretty sure I have some wire around, so that's fine. Nothing crazy, it's like, it's not a lot of current at the end of the day, at least not continuously. I don't know if bus bar is the actual word. Split power connector, Arduino. Just looking for some hobby grade thing that's not like very expensive. Arduino bus bar. It's like a power board, almost like a power. Like the other option would be to make our own custom power PCB. Power board. No. Power board Arduino. Oh. Yeah. Yeah, something. Okay, here we go. Here we go. Yeah, this is what I had in mind. See, this looks nice. Distribution board. Power distribution board. That's the word we're looking for. Let's see what we have. So this one's cheaper, but it doesn't have prime. This one looks cool. So let's see. Yeah, I mean that would also work. Yeah. 2 outputs, maybe dimensions approximately 10 centimeters. That's big, man. Dimensions. Oh, 3.9 inches, 4 inches. 4 inches is like almost also 10. Okay, we'll get this one here. It comes with 2. That's great. And I think this would basically fix our power issue with the servos. Like servos will have more than enough power, and this means we can move all the legs at the same time, all of the joints without tripping the Arduino. And of course, the PWM signals from the Arduino to the servos will still remain as they are, right? As we have them right now, which is like jumper cables. I'll add these electrical schematic. Part 4. All right, so I think, yeah, if we order all those things, I think that should be enough. Obviously, so the Arduino on its own has 13 digital pins, so that's more than enough to, actually that is just enough to power, to control 12 servos at the same time. Now, if we find, and I think digital PWM works at 5 voltage. If we find that that's not enough, we will have to look for a solution. I've never tried to power 12 servos from a single Arduino. And yes, I could de-risk that right now, but I feel, we're just gonna try to run all these things in here. What else? The other thing to keep in mind is that you probably want your Arduino and your bus bar to have the same ground, so the PWM signal doesn't drift too much, if that makes sense. But that's not going to be a problem. Like I said, we're going to power the Arduino from the 5V bus bar. And so this is going to be our electrical schematic, and I think that fixes our power distribution issues. So I'm going to mark this as done. For microcontroller, there were a lot of, on the comments, someone left, saying the ESP32 microcontroller was a great option. On Reddit, we also got a lot of good recommendations. I'm going to stick to Arduino for now, and we're going to try out some of the software smoothing solutions, and we'll have a cycle. I'll post them back on Reddit and to see the results, and maybe depending how good they are, maybe people will have recommendations on how to improve them, or maybe they're just perfect as is. But for now, I'm going to order all the parts you see here. Obviously, we already have the things to the left and to the right. We just need the connectors, the back converter, and the bus bar. And so we're going to be spending $10 on that, on the back converter. Let me refresh. $12 on the back converter, $9 on connectors, and then our bus bar is $14, right? So, I mean, not bad. We do have to track spending at some point, like I said here, because these things do add up. But so far, we're fine. I think we're fine. Yeah. Anyways, with that out of the way, with electrical out of the way, now we can move on to some CADing fun. And so the only question is, where do we start? Legs or body? And I think we're gonna start on the body. Let's see, where are we? Antarctic. I thought I had an assembly with all this stuff. Right? Thing assembly. Yeah. So this is where we are. This is basically what we have right now. One of the biggest issues was that the torso that it made here doesn't actually fit in the printer, right? So, I guess I didn't have that as an improvement. Make it fit in the 3D printer. And so I'm just going to put the hammer down and quickly, work on these things, and maybe I'll comment through it so it makes sense, so you guys can follow along. But if we just go on the body, and so this is the design on the left. On the right is what I've pre-printed. If you saw the last video, I had to make some modifications with a knife in real life, but this is what we have right now. And what I've been thinking was that we don't need a lot of the things that we had. So I'm gonna make a lot of abrupt modifications here. Now you see, if I delete these, it actually deletes the parts here. Instead of deleting them, I'm gonna remove faces, just so we can always go back if we think we got something wrong. And I'm gonna work on 1/4 of it, because we can always mirror it. So delete face. Okay, so we do not need those fillets there. I've been thinking that we actually don't need this second wall back here. I mostly had it because I think I think it just looked good, but I don't care about that anymore. Offset 0. So I'm gonna create a plane here, and I'm gonna split this part with this plane. With this plane. I'm gonna keep that side. So that's kind of like what I had in mind. We don't need that extra material, so we're just gonna go lighter weight. Let me delete some faces here. Delete face, delete face, delete face. I'm gonna get rid of these fillets here. I'm also gonna split for now. This is bad practice in CAD. Like you should just modify the part, not keep splitting, because it keeps adding features here to your feature tree. We already have 46. Eventually you add so many features, your part gets heavy, it loads slower and all that stuff. But for now, just for the purpose of this video, just so it's easier to follow along, I'm gonna add a plane here. This is one of those things that I've been like, as I look at the part through the week, I'm like, oh, we could probably remove that. So I'm gonna remove, and this is gonna seem kind of crazy, but I'm gonna remove all that portion of the torso, and really this is all that we need to hold the shoulder joint. This is it. We don't need anything else. And so with that in mind, let's this will fit in the printer. Done. And the servo mount holes were oversized, so these holes were 4.3. We're trying to screw M3s in there, or I guess those were M4s. No, those were M3s. And so if you want to screw an M3, you know, an M3, the diameter is basically, the nominal diameter is basically 3 millimeters. It's obviously smaller on the lower portions of your pitch of the screw, but 3 millimeters. These holes should be smaller, right? So it should be in like 2.8 millimeters. So they're at 4.3 right now. So we should remove them by 1.5 total. So that means 0.5 each side. So we're gonna move the face by 0.75, like I just said. And so all these holes are getting smaller, and that will fix our issue there. So boom, that one's done. Next, the walls are too thick. No action there for now. Change the servo horn. We could remove the servo horn. You know, it's like basically the shoulder joint does have this servo horn. If we remove this servo horn and we make it part of these kind of like square that houses the servos, if we do that, right now what's nice about this thing is that it's symmetric, so we can use the same one here and on all other legs. If we incorporate the servo horn onto this part, that won't be the case anymore, and each leg will have a different design. So for the time being, I'm gonna leave it as is. But I think eventually we can consolidate. Not now. Skip. So I'm gonna label this as skip for now. Skip. Reduce clearance of the shoulder joint. I did point out that the shoulder joint, you know, basically this clearance up here, in here, this gap, is bigger than necessary. And so if we shrink that gap, then this channel in here gets larger. Slightly, marginally larger, but it gets bigger, and that means we can maybe like fit some stuff there in the future. You know, easier for wire routing, or in the future, this is a dog after all, we might want to add a tail, and like we can package a tail in there. So I think, you know, we can always make that bigger. Yeah. Add wire routing. Shoulder joint. Yeah. I'm also gonna skip the dimensional stack here, because like so the dimensional stack issue was that when I was assembling the servo, it was oversized in this dimension, actually in this dimension, and so I had to push in the servo in here really hard, and it went in, but it went in because this part complied, and so that's putting strain on the body. It's really not as designed. Sorry, I'm gonna turn off the blur of my camera. Yeah, turn off the blur so you guys see better. Yeah, we don't want the structure to have to comply, to have to flex in order to come together. But you know, for the time being, I just want to keep going. So I'm gonna skip that also. Yeah. And so we have this bracket here. Now in terms of, and first of all, if we go to our top level assembly, everything's gonna be screwed up. Yeah, you see, like everything's gonna be screwed up. We have broken mates. Totally understandable. I get it. But this is what, you know, our bracket looks like. And you can see here that the clearance is, I always forget how to measure. I always forget how to measure it on shape. The clearance here is like 81, like 8 centimeters basically. What? No, that has to be wrong. Let's measure to a point here to here. Minimum distance 10 at an angle. So I think we can shave maybe 2 millimeters from there, and that's super easy to do actually. So if we go back to our torso file, if you remember, we had a sketch for these cutout here, and so if we just remove, no, that's not the one. That's not the one. Here, if we just remove 2 millimeters from these, that's all we need to do. Everything will build around it, and then now if we go back on our assembly here, you know, we previously measured 10 millimeters, now it's gonna be less. Now it's 9. So it got slightly better. Can always optimize it. There are some rules of thumb about clearances for moving parts, but you know, I think that's like a safe intermediate. As we move that wall, we did run into some potential issues here where we might not be able to fit a screw all the way here. You know, interference with our hole. So I think for now we're just gonna reverse that. Yeah, we're just gonna leave it where it was previously. Not a big deal. And so this is what our new servo bracket would kind of look like. And then we can go back to mirroring these. Of course, we mirror the part. No, the part, yeah. Mirror the part on the center plane. And this is what the combined for 2 servos would look like. And so you can see that we have this here, and we'll print another one that fits in the front. You know, it's pretty straightforward. I'm just gonna mirror it just for visualization purposes. Part. So it'll look kind of like that. Of course, we still need to, you know, polish these parts a little bit, but it will look kind of like, oh, it's not loading. I see. It's a different body. It'll look kind of like that. And so in the middle here, joining the 2 servo brackets, we'll need another part, and that part will also be what houses, you know, the battery, the controllers, in part the servos and stuff like that. It will put everything together. But I think, yeah, doing it like that is cleaner. Yeah. Trying to think if I'm overlooking something here. No, right? Anyways, let's reverse that mirror, and I'm gonna close this pocket here. We don't need that. And I think so far our walls have been 5 millimeters thick, which is very thick if you ask me. So it looks like that. And if you think of the loads, you know, maybe this servo attachment is looking a little thin, and we also got to think of like how we're going to attach all of these onto the center part. So don't have a strategy for that yet. We could attach it in the middle. Of course, if you attach in the middle, that implies that there's gonna have to be extra material here in the middle part. You kind of like don't want to do it through the middle, because if you put structural, if your load bearing features are running through the middle, the middle is also the best part to package parts, right? If you want to fit something big like a Jetson Nano, you would want to put that in the middle, because that's where there's the most room. So if you put your structurals in the middle, that kind of gets in the way. So don't want to put it in the middle. We'd rather put it on the sides. If we put it on the sides, it will make the overall torso a little thicker, And we had that whole conversation of like, oh, you want this to be a cheetah, not a donkey. But I think, you know, we can strike a good balance there. Yeah. This is concerning though. This feels very flimsy for the on the servo side of things. So we might close these. We might add some material on top of here to make it a closed rectangle. So let me do that right now. Yeah, we can do it here. So something like that maybe. And it doesn't have to be 25 millimeters, that's a lot. It can be another 5. So something like that. So I'd feel much better with that. And of course we cannot round these corners in here. We would like to, but we can't because the servo basically says it's almost like a squared edges, squared corners. So, but something like that. And then if we start to envision what this part in the middle would look like, I don't know which plane I used to create that. The top plane? Top plane. Yeah, so we would need something that basically looks like that. It touches this surface here, so we can do a coincident mate, and we need to add some space here to maybe like a 10 millimeter, like a tenner, to give it some space so we can, like, you know, make some good joints there. And this also has to be the middle of a robot, so we'll create a construction line here that goes to this origin point, which is the middle of the robot. That's how we made it in our sketches. This will be a construction line, and it will be horizontal, and so that forces the geometry so that it's perfectly in the middle. So I think something like that. I mean, for starters, you know, something like that. And so let's start there, right? So if we have that, and this is also 5 millimeters, although ideally I think we would want to go to 2. 2 looks very thin. But you know, this was 5, you know, 5, this wall was 5, these walls are 5. It's very, very thick. So actually, let me see what we used for the leg linkages, because those feel proper to me. Those are 3, right? So we can do 3. Let's try to start making surfaces 3. So that could be a 3. And this is a separate part, so don't merge. And so I'm gonna, oh no, it merged then. New, yeah, different colors. I want to make everything different colors, so it's very clear that these are different parts. You know, something like that. And then we would have to extend these, so we have some mating surfaces here. So let's move that face as well. Move face. Ideally, there's an up to, yeah, up to here. Yep. And we do that on the other side too. Yeah, something like that. And I think that starts to look more proper to me. Yeah. All right. So now we're getting somewhere, I think. Yeah. Now, of course, this guy needs walls so we can mate things to it. So from the top, I'm only gonna do half, and then I want to mirror things. So from the top, that extra 10 that we added will just, well, it can be more, because before it was -10 and then a 5 wall, and that was enough clearance for the servo. So this could be 15, and in theory it's fine. It's a perfect fit. So it could be something like that. We add it to here. It's a thin. We said we're doing 3 thickness inside. So it'd be something like that. And it'll be on the other side as well. And so we would probably add 2 screws here on each side, 2, so total 4. And is that gonna be enough? We could also add something in the middle here, right? Because this is the body. This is what fits, what keeps everything from moving, from like falling apart. And we have to consider different load scenarios. So yeah. I'm just a little redundant about adding more screws, because first of all, I don't know how many screws we have, and also, again, more assembly steps. So I would be a very big fan of like a 3D-printed snap design or something like along those lines, or like something that interlocks. Yeah. We'll do an interlock, I think. We'll do an interlock design. Yeah. What else? This, we could probably make this taller. We can make this middle section as tall as it needs to be, just to give us more room to package stuff. So it's 25 right now. We can go up to 30 to match with height, but we can, just to show, we can do 50, something like that. We can do 50, and so the middle section of the dock will be taller. Give us more room, more space. Eventually, we will want to fully contain that all inside, because electronics and stuff, the one stuff getting in there. So I'm thinking something like that. Yeah. What do you guys think? Looking good? Looking good? Now, one thing we could do is, instead of having the holes on this surface here, we already know those are very hard to assemble, right? Because that's basically how the servo holes used to be. We could move them. We can move the mating surface to the side, to this side here, and that could be interesting. Yeah, that could be interesting. Let me see what that could look like. So instead of having it like that, we could have it be something like this, and then goes here and here. And so this would be 3. that's just a wall. But the other wall is 5, so 3 plus 5. Yeah, 8. And then here, 20, something like that. Oh, we broke it. I broke it. My bad, guys. So it could be something like that. And so then these would have a feature that comes here, and then there's holes going this way. So that could also work. But I do want to add more walls so we have more material to thread into. And so just as a reminder, previously we were at 15. We said 15 is good clearance to the servos. Yeah, I could see it. I could see it. You know, one thing that I keep thinking about, it's like when you're writing code in your editor, you can write comments on each line of code explaining what it does, basically. There's no equivalent on CAD, right? I cannot like write a comment on this hole. It's like, oh, this is this dimension because of these. It would be cool if someone had something for that. I don't see an add comment section here. No option for that. So just an idea. If anyone from Onshape is listening, that'll be cool. That'll be cool, guys. All right, let's roll with this. Let's roll this. So I'm gonna delete this face. That didn't do anything. I'm gonna delete this face. Oh, okay, it's not working. Oh. Delete face. Okay, instead of deleting the face, I'm gonna remove it like this way. Solid, remove these. Yeah, so I should, I don't know why that's not working. Okay, there we go. So like that. And I do understand this is getting a little complicated, but I think it's gonna be neat. And then this is gonna be a 5. And a coincidence here. Coincidence. Okay. And then we're gonna add these here. Let me know if I'm just sounding crazy here. Hopefully not too crazy. Right, something like that. This doesn't have to be that tall. 35. I do feel a little weird talking through here, but again, let's see if people watch this video. 35, so something like that. That's still too tall. 35 minus 2. Okay. So something like this. This gap I'm gonna fill with purple material, and then I'm gonna make some holes. That makes sense, right? I think that'll work. So these we said it was 32. Okay. We need to add 3 millimeters of material here. Move face. 3. Only 3. Okay. So something like that. I don't know. I might be overcomplicating this. Yeah. Okay. And well, the other thing I was gonna add was a rip here, just a triangular, like that. Just trying to stiffen this part, which I think I'm not concerned, but we can always remove material later on. So you see how it's a different color? That's because it added a new part instead of adding a new part, instead of adding the part. So now we added it, so something like that. Yeah. Try to keep things stiff. I think that'll work. Just me, or those holes look different sizes? 3, 2.8, 3, 2.8. But we moved all the faces. I guess there were different sizes to begin with. So making those even smaller. 2.8, good. Okay, so something like that. This blue part is gonna print very fast, so that's nice. And I think we can add an interlock feature here in the middle, something that keeps things lined up. But I don't think it's fully necessary, to be honest. Yeah, maybe we do without that for now. And if we are not feeling confident, we can add it back later. Yep. All right. No. We're a chamfer team here. Team chamfer. Okay. So now we would add some holes here. Extraction line, vertical. These two should be the same. We can use equal, and maybe we'll do in 2.8s, so just M3s, split apart by 20. From the top here, I'll do like a 5, and then from here, we'll do like a 10. I guess a better way of doing that, instead of setting it to 5, it's just place it in the middle. of the face. Horizontal construction. Okay. Right, so now here, remove blind up to through all. Merge scope, okay. All right, so now we have holes there. Yep. That's definitely one way of doing it. Yeah. Yeah, 2 holes. Yeah, you gotta think. You gotta think of the loads in different axes. I mean, this is technically fully constrained. Yeah, I think this is fine. Okay. I mean, if that's fine, then the next portion is just to mirror it and call it done. I'm gonna enlarge these holes here, make them through holes, because like we don't want it to thread onto those holes. We want it to go all the way through and thread on the purple holes. So it's gonna be 3.2. It's like a through hole for an M3, a tight through hole, still a through hole. Okay. And okay, let's try mirroring it. I think I'm done here. I think it's art. Part mirror. Okay. And of course, you know, general wisdom would say add some rivets in the middle here for this part. Like I said, that gets in the way of putting things inside. Let's add like some light riveting, just in case, but it does get in the way. We can do like a cool honeycomb. JK, that'll take too long. Oh, what is this? This was supposed to be gone. Oh, it's not gone. Oh, I see what happened. So before mirroring, you gotta split it. And split it one more time. Okay. So now we can mirror it. Entities to mirror, planes to mirror, by. Very nice. And then one more mirror. New mirror. I think add it as a new part. I should be adding. So now this is all one part. All right, cool. All right, cool. Now let's finish off this bracket. So I'm gonna split it one more time. Again, you shouldn't have to split it so many times. I'm just doing things very quick and dirty here. All right, so what needs to be cleaned up? I think we can clean these up here, just for the sake of continuity. We can do something like that, where we go all the way back here. Then here, this touches here, coincident, and then here, this touches here, and it's coincident. Why not? Well, I can make it coincident to the plane, right? So coincident to this plane, it's the same thing. Coincidence, and then horizontal, fully constrained. Then you are coincident to this face, which a face is almost like a plane. No, it doesn't want to. Why not? Okay, that worked. So this is just really cleaning it up a little bit. Okay. Okay, there's extra material here that we don't need. So one way of doing this would be to just round these corners here. Too much. But I think first I'm going to move these corners. So I'm going to move the face. Move face here, and then I don't care for it to be perfect right now because I can always come back once the feature is created. Something like that. All right, so we saved a little bit more material there. And yeah, and that was basically all I had in mind. Now we can mirror this again. Mirror. Okay, so it'll be something like that. I mean, I do think it looks more, it definitely looks way, like compared to the right, it looks like way more lightweight. Way simpler, way lighter. Yeah, the mates here are broken. We need to rebuild this assembly. That won't take long. So that's there. And now for the sake of, just for visualizing what the full assembly is gonna look like, let's just, I'm gonna mirror these. Okay, so that's what our torso would look like assembled in one piece. And yeah. Now, if you think of what these purple part is, it's basically a U-shaped. U-shapes are not very stiff, not in torsion, and a U-shape can always bend outwards, right? So that's why we would like to add some ribbing, maybe like running across so the U doesn't open. But for torsion, we would like something like an X here. Now an X would get in this way of the servos that fit in here and actually sit flush or almost flush. Quasi-flush. But we do have some clearance that we could make use of. Let me hide some planes here. It's too many planes. What is this, a sketch? Hide the sketch. Okay, we have 2 millimeters of clearance there to the servos. And so let's use those 2 millimeters to just add like, I guess I'll just run them like these. Actually, I want to run them here in the edge. That's like, it's going to be like optimal. And then we could maybe, is that overdoing it? Looks a little silly. Let's see, what if we run just those? And my sketch is not good for those ribs, by the way, because if I use the thin feature, it's not going to be consistent. But just to show you what it looks like, thickness is 2 and 2. Right, so something like that. And yeah, this one got messed up. I'll clean it up in a bit. I'll clean it up now. Okay, so let's clean it up. So let's get rid of these two. Let's get rid of everything here. Let's use these rectangles here, sorry. Rectangle here, rectangle here, rectangle here, and rectangle here. And then the thickness of these rectangles should all be the same, so I'm going to put an equal constraint there, and that equal constraint is 2 millimeters. And those are 40 apart, 40 apart. All right, so that, I think that looks proper. It's a solid and it's 2 millimeters. Yeah, so now that would work. And we can always, you know, come here and do something like that. Of course, that's gonna take space that I don't know if we have. You cannot package components that you haven't figured out what if you haven't figured out what components you're using, right? But okay, that's too much. Taking space for no reason. Something like that. Okay, cool. Feeling good. I guess we also removed a fillet here. Which we could reintroduce. Let me see if that's easy or not. We could. Let's see. Top assembly. Yeah. Okay. Yeah, I think I feel good about these. So the next step would be, well, we would be ready to print, but before we start printing, let's also fix the top assembly. Yeah, look how much lighter this new part looks. Yeah, I think that's good. Yeah, that's a win. All right, cool. All right, so let's see. So now we're calling that done. Let's see what's broken here. So cylindrical, that's good. So what's broken? So here to here. Okay, why is this one broken? Mate connector. Okay, so this one's easy broken just because it goes here. It's here. This is the one here. Yep. Okay. What about this one here? This is a mate, an offset mate. Yeah, this one's not coming back. What about this one here? Oh yeah, this I haven't reintroduced it yet. Okay. This still looks not happy. And it's because we might be on a named position. We don't have any named positions. So what is completely fixed? Let's see. Part 1 has degrees of freedom. Shoulder horn has degrees of freedom. This is fixed. Okay, so if that is fixed, we can start building around there. So I'm gonna insert the parts that we just created now. So I'm gonna insert these, and then gonna insert another one of these. No. Interesting that that's how the insert works. Yeah, so when you click more than one part on insert, it actually starts inserting multiple of them instead of canceling the previous insert. Done. All right. So with this part in mind, this should be a pretty easy thing to do. We click M for mate. We do a planar mate between this face and this face. Of course, the previous face wasn't selected. We go here, select it. And then if we mate these cylinders, that should be it. So there's one, and then there's the other. You need two to fully constrain it. And it's like, that's it. And so now this purple part is fully constrained. The one thing that comes to mind is that servo wires are not gonna be super happy. They were not super happy to begin with. Maybe a little less happy now. Oh, also this is not the final position of the servo, so never mind, never mind. I don't know why this guy's not moving. Let me look through the mates here. No, that's not correct. So there's a mate between that and... I cannot tell what's getting mated. Oh, the servo. Okay, bad mate. Instead, let's constrain the servo with the proper mate, which is a cylindrical mate or the servo mounts. So, boom, like that. Okay, servo wire is not like looking happier now, way happier. We did make the robot a little wider, but it's 1 centimeter, no one can tell. Yeah, and then we can constrain this guy as well. Check for clearances. We did reduce clearances, but you know, there's still so much clearance. Actually, we rolled back the reducing clearance to not screw with these holes, actually, so that explains it. Okay. Planar. It's been an hour and a half so far. Time flies when you're having fun, huh? Where'd everything go? All right. I literally do not know where the part went. Oh my god. Yeah, the part keeps disappearing. Like it didn't disappear, it's just really far away. So I'm gonna like add a new one. That's what happens. Parts don't want to play ball, I remove them and I add a new part. Replace them with a part that actually wants to be here. I learned that from the Mr. Beast handbook. You have A player parts, B player parts. Okay. I do wonder how long till AI can just do these for us, and I don't have to do a million mates manually. But anyways, so that's a torso fully assembled in our top assembly now. So that's kind of like what we're looking at. Looks like there's plenty of room. I mean, for the Arduino configuration and the bus bars and the battery, everything's gonna fit here, it's fine. For the future where we might want to add like a Jetson Nano, it's not gonna fit in here. I'm just gonna make the profile part taller and we'll have like 2 levels to it. And I think that'll just be fine. Even now we could have 2 levels to it. Also, by the way, I'm out of filament, so parts are not going to be green anymore. This is the end of the era. We're going to move to orange now. Okay, so now let's fix these mates. Let's see what's broken here. Okay, so missing mates, basically. Okay. Is that fully constrained? No, not rotationally. 1 more cylindrical. It's kind of weird. Sometimes it's like you gotta double click it or something. It just doesn't register sometimes. On shape just doesn't feel as robust. Okay, cool. Cool. Yeah, okay. Seems to work. Seems to look, I mean, looks good to me. There is no servo horn here. I guess I never added it. And so we could start printing parts just because it's going to take long, or we could just not print yet and let it simmer and move on to the leg and just finish the leg. So let's see, let's look at our to-do list here. We skipped wire routing. We finished servo mounting oversized. We make it fit in the 3D printer. We need to add the mirror legs. So let's jump in here. Let's jump in the legs here. I think the torso is basically, that's the next revision. That's done. That's ready to be printed. So if we jump on the right leg assembly, I'm gonna take a bathroom break, BRB. All right, so we haven't touched the leg in a while, so let's see where this is at. So we do have name positions for this guy. I'm gonna go to just chilling, and okay, it's completely broken all the way up. Chilling is applied. Okay, we have broken mates here. We don't have broken mates anymore. Cool. Okay, so let's hear cross-section view. So I think on CAD we still have, yeah, we have a snap rank here that we can remove. We don't need. What else changed? I guess that's the only thing that changed. There's also the fit of this thing here, which is not, it's not critical, but since we're here, we might want to change it. So look, let me section view it. Okay, yeah, so you see here, this was like my hacky way of removing the two bearings that were in here, the linear bearings. And so you can see here I have a lot of clearance between these parts, this gap here, and that's just because I didn't know how big to make it, and it worked, but there's a lot of play, and I actually had to put a screw through it. It's the same as we have in CAD. But I think if this joint was a little tighter, we could essentially do without the screw. So for the next iteration, so let's see what we have here. So we have a 9.6 millimeter outer diameter boss into a 10.6 millimeter. So 10.6 minus 9.8. It's 0.8, so 0.4 clearance on each side. So I think we can half that. We can half that, and it might be better. And axially, our clearance was 0.5 on each side. We can also half that, and it'll be better. So I'm gonna go in here, and well, first of all, okay, it's loading. Okay, so we can just use the move face feature here and bring this by, we said 0.25 on each side. So on each side, and then we said we would also change the this by 0.2 on each side, and just like that. And so if we go back in here and we do a section view. Hi. Good. I'm recording. Yeah. All right. All right, so now that's a 10, and this is a 10.4, so 0.2 on each side, so it's much tighter. So I think that'll work. I was gonna do trial prints to try it out, but I'm just gonna go with it first shot, see how things turn out. So let's remove this, turn off this section view. Next, the one and only other change that I wanted to make was, actually, there were two changes that I wanted to make. So improve joints. So that was what we just did here. So I'm marking this done. Remove supports. I guess the biggest thing to remove support was getting rid of these pockets here, which we could do. They do look nice though. but yeah, I guess I can remove those. Let me see if that orange part can be modified. Some parts we can modify because they're imports, but yeah, see, this part is an import, so that's not going to be easy to modify. I would have to recreate it, which is fine. I can eventually recreate it, but for the time being, don't need it. So gonna not do that for now. Skip. And consolidate bearing removal parts. So let's do that. So that's basically where we were before. So in order to remove that bearing from the hip, I removed the bearing and added just a placeholder, kind of like a slip ring, just to fill in that void. But at the end of the day, it's plastic on plastic, and if this plastic part was part of any other plastic part, it will be fine. We do need to think about this because this plastic part does lock this arm with respect to the cam here. So, but also, yeah, I guess we could leave it as is also. So also gonna skip that. We'll call it tech dead. Maybe come back to it later. Just rushing towards getting the full dock. So now what we actually have to do is mirror the leg. So this is the last part before everything else is either skipped or done. So let's do that now. Yeah, and so if we look at the leg here, what needs to be mirrored? Basically, this component would need to be mirrored. This guy here, the upper, is the same thing. It just needs to be rotated, I think. What else? This is the same. So I think we can copy that assembly. We can duplicate the assembly, and we can, if that's the right leg, the other one's gonna be the left leg. Where is it? Lower leg. Yeah, I lost it. It's not here, right? I guess it's part of these, lives in here. So it's all the same thing. So I can go here and I can duplicate. And then we have a copy, and then we can change these to left leg. And I don't need a lot of these mates here. Don't need the fasteners, just for the sake of speed. Don't need the fasteners. Can do without the fasteners. No need for fasteners. And we can, I guess this is the first thing that needs to rotate. This guy is fixed. And so this guy would need to rotate 180 degrees. Except, let's get rid of all the fixed parts. Unfix it. Okay, so now this guy needs to rotate. Still not rotating. Degrees of freedom. Now we can delete this part. Don't need it. Okay. Okay, there we go. 80 degrees. 180. Okay, so that's the starter for left leg, and now we can fix this. Okay, so I think, okay, just look into the right leg here. So the hip goes on the back side. Guess that's correct. Back side. Yeah, okay. This is correct. This looks fine. This, not entirely sure yet. I'm gonna do some mates here. This planar mate. Basically, I just want to double check that we're not missing any parts. Oh, by the way, another thing I wanted to change was on the leg was add hard stops. So when the leg maxes out right now, there's some random clashes that are like, what actually stops is like here, this edge here, and it's worn down over time on the actual leg, which is not perfect. So we eventually need to come and fix that. Yeah. Now the one part that does need to change for sure, maybe not. I was gonna say it was these, but it looks fine. Could that? I mean, if that looks fine, I'm doing something wrong. Yeah, I must be doing something wrong, but I mean, let's go figure it out. Looks like there's no midpoint mates to mate things in between a plane, but I do know that this clearance here is 0.25, so we can mate it like that. And so there's no way this is correct, right? Because it's basically the same as the right leg, and it should be on the left. Yeah, there's no way that's correct. Let's just add it to the body. I'm pretty sure I'm getting it wrong just because there's no like plane of reference. Board Studios assemblies left leg. Yeah, it's completely wrong. But I'm gonna add it here just so I can use it as plane of reference. So we said the hip goes on the back side and that on the front. Okay, so first of all, this orange part needs to change. So it is a different part. Wait, is it a different part, or are the servos just, they just, so the hip is back at top, the hip is here front and top. If we were to rotate it, it would be back and top. So we just need to rotate that part. So hip needs to be back and top. Hip is back and top. Back and top. except this is the back side of things. So this guy, I'm doing a lot of shape rotating in my mind right now. Back and top. I mean, it's back, it's just not top. Can we be back and top? Back and top. Yeah, we need a new part. Yeah, okay, cool. At least that's clear now. Okay, so let's see what we can do. Maybe, because this part we imported from the Dingo CAD, so we can modify them, but I'm sure they did mirror it, and so it's this part here. I just don't know if I can extract it. Can I copy it? No. Can't export it. Okay, I'm gonna copy it. I don't know if this copy pasting thing works. Can't paste it. I tried. Okay, can't paste it. Can I mirror this part? Is there even mirror? We're in an assembly, so there's no mirror. And it looks like I cannot export it. Oh, I can export it. Okay. So in theory, if I export as a step file, and then I re-import it, I should be able to modify it, right? So I can insert okay, I guess I have to go here and I have to import it somehow. So I can create import files. There's a step here. Cool. So now I can mirror it as a part. Add part, mirror plane here, right? And then no, new part. I can call this left servo hop. And so now I can go back to my other part. This is getting very complicated, but I think it's a good solution. So now I can go here and insert. Insert this guy. And okay, I must have mirrored on the wrong plane because these are the same thing. But let's open this part. Okay, okay, let's see. I mean, that mirror makes sense to me. I don't know why that didn't work. Let's try that again, I guess. Insert. Can I just add it here? I'm gonna add it here so it's in here somewhere. So now it's here. I'm gonna call this the left servo hub. And now same exercise, I'm gonna mirror it. New entity, mirror plane, this one right in front. So it's a mirror, and then we delete the original. And so I think that should do it. Insert. Insert. Okay. Yeah. Okay, finally got it right. Okay, great. Okay, so now these can go away. So I'm gonna fix this part and rebuild the assembly around that part. Yeah. Okay. I guess we start with the servos here. This is gonna be a lot of mates, guys. You know how the mates are. It takes a long time. This guy needs to rotate 180. Doesn't want to rotate. Okay, well, we can work with the features that are willing to work with us right now. Made it here. What if I just get rid of all the mates? Obviously, except the ones I just added, but everything else it's just being painful right now. Can I get rid of all the mates? Rebuild the legs from scratch. It'll be faster, I think. Okay, so this guy, servos. The reason why, so mates can seem very painful, right? It's like, oh, a lot of clicks and stuff like that. I've always been a believer that if putting the mates in your assembly seems painful, then assembling the part is gonna be even more painful, right? You're sitting in your computer, very comfortable, clicking away, and you're complaining. Imagine the guy that's gonna be like screwing this thing together at the assembly at a factory shop, a factory floor, right? So I've always thought that don't complain about mates. If you think the mates are so bad, you should simplify your part, because again, mates in CAD way easier than mates in like an actual part. Like putting together mates with your hands. Just food for thought. And yeah, I am complaining about the mates. I also complain about assembling this thing, to be honest. Is this the right? I guess. Okay, so servo horn going in, cylindrical. So yeah, so something like here and here. Yeah. Okay. Getting somewhere. Okay, well, this is the one fastener that we will keep. Every other fastener I've deleted for now, because do we really need them? Like, the answer is yes, we do need them, especially if more people are going to be assembling these. But when it's just me assembling it, we kind of don't need them. Okay. I think this is supposed to sit in here. Like that. I don't know why this is not rotating. I'm gonna remove these for now, because like, yeah, it should be rotating. It's not rotating. Okay, that feels better. I guess this is the other part that needs to be mirrored, right? Because it doesn't look fully symmetric. It's not symmetric for sure. So that needs to be mirrored as well. So it'll be like that, like this. This part also needs to be mirrored. Yeah, mirroring the leg is starting to be like more of a pain than I anticipated. Okay, this one needs to be mirrored, but don't need this for now. Don't need this for now. Don't need that for now. Okay, so let's mirror this part, servo cam. So let's mirror, and this is mirror plane, this plane should be fine. And we're gonna call this servo cam left, servo left, servo cam. And I think we can just have the two parts in one file. Hopefully, yeah, it doesn't destroy things. And then we're gonna insert, again, I don't know where this part lives, other documents somewhere. I guess here, and then we have the left one. And then we can, on shape. Okay, we can, okay, just like that. Wait, did that make a difference? Did that actually matter? So the more roundy part should be in the back. Yes, perfect. All right, so now we do cylindrical here. Planar mate here. Another cylindrical. Here. Cool. That's not what I said at all. Oh, it crashed. Okay, first time we make on-shape crash, so that's good. Achievement. Okay, please explain to me, how is this even possible? I don't know. Okay, anyways. Cylindrical here and here. Yes, perfect. And let's see the cross section 1 second. It will make way more sense. I see. Okay, so if I'm reading this correct, there should be a planar mate here. Of course, I click on it, nothing happens, you know. It's like, look, I click on it, okay, now it happens. I can't see the snap. Okay. Look, okay, planar mate, look at this. I click on it, okay, now it works, huh? I guess I click on it, nothing happened. Click on it again, it works. The only way to make on-shape work is to shame it. And then it works. So, okay, so it's like this. This is the top, this goes here. Then this cylindrical mate here. I remember in school when we were, you know, I've been in a few teams. We built race cars, we built submarines, we built drones. No one would ever want to place fasteners on their assemblies, and I always wonder why, because I really enjoyed it. Like back then I used to love CAD, and I kind of like understand now, I guess. Like It's actually kind of annoying. This actually takes a million clicks. Of course, I had nothing else to do. Like this was, I was like, yeah, why wouldn't you want to spend all day on CAD? It's great. I'm practicing empathy now with my old classmates. I understand you guys now. I'm sorry. Sorry for telling you had to include every single fastener. Now, on the other hand, including every single fastener is actually great for BOM management. You know exactly what parts you need and how many and why. There's nothing worse when you are assembling something in real life and you missed one part, or you spend money that the student teams do not have on parts that you don't even need, which happens actually quite a lot. Okay, this is almost done. We just need to mirror the lower, and that's done. And then for the first time, we can say that we're ready to print the entire dog, everything, the entire dog. Now, of course, we can't move it till those electric components that we were discussing about earlier get here. But I mean, that's not going to take too long. Right. Okay, so now we mirror this part. We could also just YOLO and don't mirror it, but no, we're gonna mirror it because we do things the right way here. We don't cut corners here, okay? We don't rush through things. We don't rush towards goals. All right, we do things the right way. All right, so rename these to left, lower. Okay, perfect. And we can remove this part here, and we can do an insert, and then we can go find it. This is it. The left lower. Cool, right? Cool. All right, cylindrical mates. Here we go, cylindrical, cylindrical, cylindrical. Cool. And like, let's go for the, there's no middle plane mate for some reason. Pretty lame on shape, but we know what the offset is, and it's bad to hard mate your offsets because what if they change? But that's what we're dealing with. We're dealing with on shape, guys. Gotta do what you gotta do. Like I said, if we get enough views, maybe we can get a SolidWorks license, and oof, development's just gonna like skyrocket. We're gonna move so much faster. All right. Okay, so something like that. Just doing this for fun, really, because who cares about the tip-toppy thing? Oh, we do gotta print it. Okay. Planar. Okay. All right. That's a left assembly leg assembled with no fasteners. Just bare bones. And so if we go to the top assembly here, okay, refresh. All right, perfect. Okay, so remember the hip goes on the lower, on the back, and the higher side of things, and then we can assemble these by doing a cylindrical here and here. And I guess a servo would be nice, so we just copy this servo. This is our servo here. The horn is to the outside, so we rotate 180 And we do some planar mates, more mates. We're not quite done yet with the mates here, but you know, it's gonna be good to have a nice one-piece assembly. So that's that. We have cylindrical. We have another cylindrical. Okay. By the way, one thing I noticed is that the servo clearance is too much here on the upper side. You see that? It's too much clearance. It's too much material. We can eliminate some of that. Definitely have too much. Okay. The other thing is constrain axially. I actually don't remember how I constrained this guy. SolidWorks, when you click a part in an assembly, it highlights which mates are relevant to it. Onshape doesn't believe in that because, you know, it'll be too convenient, too easy. It's better just to have you guessing. And so, oh, which mate could it be? And just you have to click through all of them. But it's not that bad, and it's good exercise for your finger. It's like cardio. So yeah, that's how you recognize an on-chip engineer. They have beefy fingers. So this is true. I'm not making this up. All right. So this dog has 3 legs now. It's a little sad. We need at least 4 legs to feel good about the dog. This dog is too young to only have 3 legs. Alright, chilling has been updated, so now we can go here and we can set this to chilling, and it'll be chilling. Boom! Alright, you guys like that? Easy, right? Easy peasy. Okay, alright, so now really quickly, just gonna do the same thing on the front. Quickly being the keyword. I really wish I could have music playing. CAD is one of those things where you're not really using, and I'm speaking here for my own personal experience, maybe you're different, but you're not really using a lot of brain power. You're just like clicking away. And so you can just put music and turn your brain off. Whether as things with programming, I mean, it really depends what you're programming, but I feel like you do need to use the brain more. Let's see. Okay, cool. And then we're gonna go ahead and insert another leg. I also don't know if you guys noticed, but I have been using different YouTube thumbnails. So I'm gonna need a thumbnail, and obviously this guy is going right on the thumbnail. Or we just print everything and assemble it, and that's the thumbnail. But I feel like assembling everything together should on its own be a video, because it's kind of like the whole thing we've been working towards. All right, for the first time, our robot has 4 legs. Let's take a moment here. This was a lot of work. Was it worth it? I think so. Yeah. So picture an Arduino Uno and a battery. It's gonna be very packed, very packed. All right. So the next step is to start generating parts that we can print. And yeah, we still have some time today, but printing this is gonna take, it's gonna probably take like a half a day, I think, every single part. So yeah, but we can get started. I also wanna clean this up a little bit, the torso. So yeah, we have 5. 5 is too much. So let's I'm gonna do 4.5. It's a little clearance. Did that not refresh or just me? Okay, there it is. All right. And what else? I mean, the one thing that would be nice is to have an enclosure for the torso, like a roof, quote unquote. So we could really quickly do that. But I think that's just going to be wasted plastic. All right. Thumbnail. All right, that's cool. Let's open Bambu. So what I can do here is prepare, and I think you can prepare different plates. That's how they call it. Or projects? No projects. Plates. Yeah, so it kind of saves them like that. Okay, so for example, for the new torso here, we would have this guy. So this is I'm gonna call it torso middle section B1. B1 as in print 1. Torso shoulder bracket P1. P1 as in print 1 makes more sense than B1 as in print 1. So it's going to be P1, and I'm going to export these. To print 3D print, it goes with STLs, and you save them wherever. Go prepare. You delete whatever you had there. Delete. That's not it. Okay, so I guess you gotta export one at a time. Yes. P1, yes. Okay. Okay. I mean, obviously, it feels like we can definitely fit maybe like one of these guys in there at least, right? We could probably show off even more if we like print out of funky orientations, but we don't want to do that. We're not that desperate. Scale. There's something here for rearrange them yourself, right? I mean, that kind of fits. Where's the bottom where like I just press it and it figures out how to make it fit? Auto orient. I don't know if it's gonna fit, but also I don't know why I'm doing this manually. Can it just do it for me? I mean, I'm sure there's a way, I'm just doing it wrong, right? Anyways, I'm gonna do that. And we're gonna get started with the leg here. So we need, this is the right leg, so we only need one because we already built one. It's sitting right here. So we're gonna have one green right leg. I'm gonna create a file, right leg P1, upper P1. Okay. Things that I've exported, I'm gonna hide. Export. Lower P1. Lower P1. Push right upper. Okay, lots of clicks here, just saving things. Push right upper P1. Yep, feed P1. Cam P1. It's a retaining ring thing. I really want to delete this thing. I just think once we actually have the full doc, I don't know when I'm gonna fix these little things. Push out small P1. Honestly, probably never. Servo hop P1. Okay, and on top of that, we just need the servo horns, which are not here. Servo horns are here. Here. We need this one and this one. So this one is the this is the knee horn, and then this one is the hip horn. Hip horn. Hip horn P1. Export. Knee horn P1. And then we also have the shoulder horn here, so might as well print that. I also wanted to tighten these holes a little bit, so we're gonna move face. We're gonna do like 0.2s. I'm not guessing, I actually measured. Yeah, see 2.8, perfect. And I'm never guessing. It might look like I'm guessing, because I'm like, oh yeah, that looks right. That's just how I normally talk. Everything's very precise here, guys. All right, cool. Cool. All right, so now we can start printing the first leg and a bunch of torso parts. Okay. Yeah. No regrets. That looks good. All right. So back to Bambu. Let's add some of these parts. Right legs. Shoulder horn. We need 3 of these. So these prints are going to be fully loaded, really. 3 of these. All right, what else? I'm gonna mark these green, red, blue when they're done. These horns for the knee, we need 3 of them. They're the same left and right, so there. These hip horns, we need also 3. Because again, we already have 1 and they're the same left and right, so 3. Servo hop. Yeah, we just need 1. And I did say I was gonna get rid of the cutouts, like this cutout here, but I guess I'll leave it for now. Because we're already here. We're printing, guys. We're printing. It's happening. Things are happening. Push rod small. So we need 3 of these. It's same thing left and right. And okay. Retaining ring. We also need 3. It's the same thing left and right. Well, is that too much? Arrange all objects. Oh. So I guess you can put them on separate plates, which is interesting to me. So it means we can fully load it. I wonder, I guess Bambu is very smart and it's like, it'll tell you, oh, clear the plate, remove your parts, and it starts the next one, right? That must be how it works, right? It can't be like, oh, it just has like something that where it like tries to sweep the plate. Okay, that one we just need 1. Feet, we actually need 3. Push rod upper, also need 3. Yeah, I don't know if it's a smart thing to put everything here in like 1 file. I mean, that's what's happening, but I don't know if it's a smart thing. We're gonna roll with it. But if it backfires, just remember, I was like, oh yeah, maybe that's not the smart thing. It's still on me to fix it. No one else is gonna come fix it, so. But just remember, I was like, yes, not smart. This guy here, we need 3 of them. Yeah, boom, okay. Okay, so I imagine we're at like 3 plates now. Let's see. Yeah, 3 plates. All right, well, let's keep adding parts since we're just doing it all in 1 run. So now the left leg. And so this is taken care of. This is taken care of. This is taken care of. Okay, so we need the lower. Taking forever to print. Left leg P1, saving that in as a folder inside. So left lower P1. I feel like, I don't know, does anyone else make YouTube videos about these? It's like not the most captivating content right here. But you are captivated, right guys? You're enjoying this as much as I am. Left servo hop P1. And that's it. Those are all the parts. Everything else, it's already accounted for. So big moment for our YouTube videos here. We've never been this close to having a full dog in the house, full dog. Oh, the one thing we're missing, oh actually, okay, let's just keep going. Torso, shoulder bracket. Okay, so we need a couple of these. Yeah, a couple of those like that. We also need servo hub. Couple of these. It would be nice. These servo hubs are so similar between left and right that it would have been nice to like mark them somehow, so we can tell easily with the eye which one is which, and so that they do not interfere with each other. Same with these cams, you know, to the naked eye they look very similar, so it'd be nice to add a pokiyoki or something like that. Again, just making assembly as easy as we can. All right, rearranging, I think we're at 5 plates. 5 plates is a lot of plates. Okay, it is 5 plates. Now, there's a lot of spacing between. I feel like if a human was slicing these, they would. Oh, 0 means auto spacing. There's no such thing as auto spacing, man. 1. It's like, compress it, you know? Where's the efficiency? Okay, now we're talking here. Okay, well, I mean, if one print fails, it will be painful. But, you know, why would it fail, right? Hope you realize I'm joking. No, I'm fine with this. I trust the Bambu. It's an amazing printer. Let's see if we can preview it. Cost, total time 2 hours for this plate. Six and a half hours for this plate. $4 hours for this plate. I think that's fine. Okay, now if you look at the filament, this plate is 215 grams. This one 178. Yeah, so 400 basically plus 81. So that's half a filament roll, which seems fine by me. So we're gonna start printing the smallest one possible. I'm gonna go get dinner, come back, print the big one, and then tomorrow morning I'll print the last one, and then that'll be all of it, right? I think so. All right. Anyways, thanks a lot for watching here. I'm gonna start prepping the printer. We do need to change the filament. I'll record that just if you want to see it. I'm super excited for these dogs. Look at that. That's gonna be so sick, you know. Just having these, like, you know, I feel like it looks so cool. Every time someone comes to my house, they point it out and they're like, wow, that's really cool. I've seen it so much now that I'm like, oh yeah, whatever. Now we're gonna have a full dog, that's cool. Very excited to see it moving around and walking around. That's gonna be so cool. I want to walk around my neighborhood. It's gonna be awesome. All right, so I was changing the filament. I forgot to record, but basically this is the new filament. It's this orange color. The previous one we have a little left, but you know that's not good for anything at this point. So pretty straightforward to change the filament in the Bambu. There's literally a thing here where you just click load and unload. I don't have an AMS. If you have an AMS, it's probably even easier. But I'm just gonna hit print on the first part, and yeah, and Bambu works so easy. It never fails. So I'll put the camera. I'll do like a little time lapse till I leave for dinner. But other than that, we should have the full robot, all the parts for tomorrow, and we can assemble maybe Sunday night, depending on how the weekend goes. But yeah, very excited.
2,000 years later.
Hey guys, it is now the next day and look what I have here. So we actually managed to print all the parts in one night, which is excellent news because it means that we can print the entire robot in basically just one day, less than 24 hours. Now the first thing that comes to mind is that the previous robot was green and we said this would be orange, but I don't know how it shows in the camera. This is more of like a peach color, so it's very peachy. So it looks like very soft, like baby peach kind of thing, kind of baby orange kind of color. But the size looks great. So this is, I already basically put these things on. The size looks great. You know, these extra ribs that we added, like this part still flexes a lot. So I'm glad we added those ribs. And in torsion, like we were talking about, it still flexes quite a bit, but I think it's gonna be fine. The only issue with these so far that I think we're gonna have, well, also the other thing is like I was saying, like on CAD, it's basically impossible to tell apart which one is left, which one is right for these parts that are symmetric. This one you can kind of tell, but it's hard. You have to like really look at it. And then the other thing is, when we were designing this joint here, we were talking about, you know, we basically have 2 screws on each side, and then we were talking about having a positional feature here in the middle to kind of like help mate things and line up things. And first of all, that would be useful. But the other thing is, once we clamp it, once we screw it in the sides, you can see here that on the center it can sag. Because, you know, basically this material is very thin and it's only held by here, by the sides, so these can actually sag. So if we put something very heavy, suddenly this surface is not going to be flat anymore. This is going to be basically arching out. So that's one thing that we could fix. We could add a positional feature. The other thing I was very happy with was we tightened this joint, right? So we said we wanted to remove the screw, and we removed some of the clearances. And first of all, it's a snap-on, right? So the way you assemble this is you basically just slide this into like here, like so. And it just, there's a click, locks into place, and there's your joint. And this joint is actually much more stiffer. There's much less play. I'm like trying to shake it. There's basically no play. This is a really good joint. And also this is actually very hard to remove. So I don't think we need a screw here. So that's great. But yeah, so for the most part, this is all the parts that we need. We can start assembling the full robot. So yeah. The other thing that I didn't mention before was that that I need to add to the schematic was a voltage monitor, right? So if we go back to the very basic schematic we made here last night, we have our battery going into our buck converter and the servos, and then the Arduino draw power from the buck converter, which is fine. The issue is that with LiPo batteries, with any battery really, there's a minimum voltage you don't want to go under, and in this case there's nothing monitoring that voltage. So you can get one of these things. They're usually used on drones, and this connects to the battery charging circuits. So it's not the XT60 we talked about, the yellow one. It's the white connector coming off the battery, and so you can plug this in and it'll tell you the voltage, and if it goes below I think 2.8, it starts beeping. And you can get 5 for $13, so it's a good deal. And I'm going to add it to our schematic here. But with that in mind, that's basically everything we needed. And so the next step will be to assemble the robot. But I'm going down to Monterey for the weekend, so I'm not going to do that today. And so I'm just going to leave this video here, cliffhanger. We have all the parts. Yeah, now we have all the parts that we need to assemble this thing. It looks great. And on the next video, we'll for sure 100% have this assembled, full dog, joints moving and stuff like that. Hopefully all the power components should be in here by tomorrow. So yeah, next video.